In order to pursue it, we simply need to be a little more careful about notation. That when we look at the notation for the S process and the R process, what we have is that in the Black-Scholes differential equation, the coefficient of the derivative with respect to S is this. That's the coefficient of the derivative of the security. I call it C, with respect to S. This is the corresponding coefficient in the bond equation of the derivative of the price with respect to R. In other words, the first derivatives. And the question is, why do these look so different? So we're just going to retrace our notation a little bit and follow along on paper if it's not clear. So we have a Black-Scholes process, and we have a bond interest rate process. So S and R we can think of as the driving processes, and then we look at functions of S, functions of R. But these are what's driving everything. And we have some notational differences, and if we now account for that, in the a bond model, the drift term is A of R. In the Black-Scholes model is A minus delta, alpha minus delta times S. Similarly, the coefficients of the dz terms are sigma of R or sigma times S. So that's what we can make our notational shift. And the point here is that if we could have derived the Black-Scholes differential equation using the approach we just used for bonds. You recall we derived the Black-Scholes differential equation by creating a portfolio of options, stock, and T-bills. But what if we developed that same equation using two different options? In other words, using the approach for bonds. In bonds, we use two different bond prices. What if we use two different option prices? The answer is the identical development we just saw would have occurred. Notation would have changed, that's all. We would have concluded that every option must have the same Sharpe ratio. Every option, every derivative security on S must have the same Sharpe ratio, and we would call it phi of S little t. Now, we know this anyway because they're all perfectly correlated, same dz, that all options have the Sharpe ratio, same Sharpe ratio. We've developed this using other tools. But if we use the bond approach, creating a portfolio with two options on S, we could make it risk-free, and we would have concluded that every option has the same Sharpe ratio. And that conclusion would have given us a new differential equation. And this would have been the new differential equation. And it's interesting to look at this and say, this doesn't look like the Black-Scholes differential equation. If, in fact, we developed a portfolio, a risk-free portfolio using two options instead of an option and stock, we would have got what on the surface looks like a very different differential equation for every derivative security on S. And we need to think about, well, why is it? It can't be that every derivative on S is going to satisfy two different differential equations. There's got to be a connection between this form of the differential equation and the differential equation we originally got. And the connection is that in the case of stocks, we can actually determine what phi is. In the case of bonds, we can't. So I'm giving you the punchline. We're now going to verify this. But the insight is, if we just started with two options, this is the differential equation that we would have obtained that every option must satisfy, every option on S. However, we're now going to see that we can determine what phi is for a stock. We can't determine what it is for a bond. The market does that. But for a stock, we can determine it, and we're now going to do that. And once we put in that determined value, this equation is going to reduce to our original Black-Scholes formula. Now, how are we going to determine phi? Well, actually, we know a very simple security that must satisfy this differential equation. It's the price of a prepaid forward. We saw this earlier, that a prepaid forward on S is a derivative security, and therefore it must satisfy the equation. If we put this price function in this differential equation, do a little bit of algebra, we will include that phi is alpha minus r over sigma. That phi, for the purposes of stock, the Sharpe ratio is identifiable by the coefficients in the S process. And when we use this value of phi, or phi, in our differential equation, that mysterious coefficient that looked different reduces to the coefficient in the Black-Scholes equation. And when we do that, we get the original Black-Scholes equation. So what happens is that what we have is that the Black-Scholes differential equation would have been derived to look different initially if we had used two derivative securities instead of one and a stock. But that different looking differential equation could have been simplified by the observation that we know a simple security that must satisfy it, and that knowledge tells us what phi is. And once we know what phi is, we put it back, we get the original equation.